welcome to Cambridge, and of course, welcome to the Computer Lab. My name's Robert Harl, and my job this morning, I actually have multiple jobs. One is to take you through this course presentation. Then there's a sample lecture afterwards, which unfortunately is me as well. So you may want to get out as quickly as you can after this one. So what I'm going to do is take you through a little bit of the history that we've got. Not too much, don't worry, it's not a terrible, boring history lesson. We're going to talk about our course as we've structured it, try and convince you that it's a good idea to do it, although I have a feeling that many of you have already made the decision at least to do computer science. Maybe I'm trying to convince you to do it here, I'm not sure. And then we'll have to talk about how you actually apply, how you go through this process, the special bits that are related to computer science. Okay, let's get going. Or at least he says let's get going, and then the clicker doesn't work. Wonderful. Let's try it on this. No. Hang on a second. Always test everything. As you saw, we were doing loads of testing before, and now this is not going to be happy. We'll get there. Okay, there we go. Sorry about that. So what we're going to cover, as I said, a bit of history, what computer science is as a subject today, the tripos. Tripos is a stupid name for 3-year degree that we have here. You're going to see throughout this presentation that Cambridge is full of stupid words that don't make a lot of sense most of the time. You sort of just get used to it and blind to it the longer you are here, but there are stupid words, and don't feel embarrassed if I say something that you don't understand. Please just put your hand up and ask me for clarifications, and then we'll talk about the actual applications. Now, some of you, most of you, are going to fall asleep in the next half an hour. So this is what you need to remember. This is the only slide you actually need to remember. Cambridge, great. Cambridge Computer Science, great. Employability, great. And then you should apply. Okay, if you're sitting here in front of me, you're already good enough to do this application, so you should do it anyway, because why wouldn't you? We will come back to that. Okay, again, I'm promising you this isn't a really tedious, long, day-by-day account of what's happened with computer science at Cambridge, but I'm going to do a couple of slides because it's fairly important. The thing we like to remind everybody is that we actually started in 1937. For clarity, I was not around. 1937, so almost 90 years now. And computer science didn't exist as a subject. It actually started here as part of the mathematics department. We were a subset of the mathematics department back in 1937. No one had the notion of computer science. But what happened was the team built EDSAC, which was the world's first usable computer. Obviously, the more adjectives you put in front of something, the more you can claim it's the world's first. But in this particular case, it's important to understand this was actually a game changer. There were other computers that came before this system, but those computers typically blew up after computing one thing. They were more proof of concept than anything else. What EDSAC did was it brought along the ability to do stored programs and consistently do these things without blowing up. And we get pictures like this one, which is one of my favorite pictures. What you see on the right-hand side is a whole queue of scientists, because they were the ones who obviously wanted to use this compute power. And you can see at the front here, a chap who has a piece of paper sort of just unfurling onto the table. That piece of paper is a whole series of punched holes, which is the program and the output and the input for the computer, for EDSAC. And they would hand it over to the person on the other side of the desk, which, rather weirdly now, that person was called the computer. That person would take it off, and you would come back after a few days, maybe even a week, and you would come and say, hey, how did my computer program go? Or how did my program go? And of course, you'd be told, well, it crashed. And you'd go away for a few more months, trying to punch a few different holes in, trying to work out what on earth had happened. And eventually you get something that ran. Sounds tedious. It must have been tedious. I didn't do it myself, but it must have been very tedious. Now, why was this actually a game changer? Because all of these people were able to access this compute power, even though it was slow by our standards, and probably by their standards, if I'm honest. They were able to do things no one else in the world can do. Now, when you look back at all the Nobel Prizes that have been given to science in Cambridge, at least in this period, you realize many of them were absolutely pivoting on the fact that they had this ability to do computation that no one else in the world could do. So that was our origins. We built this EDSAC. So 1937 founded. It took 20 years for the dark side to catch up. MIT, over the other side of the pond, 1975, right? It's almost 40 years before they were able to see the value in what we were doing and what other people were doing in this space. And over the years, well, we were the first computer science department. We were actually also the first then to realize this is an actual thing that isn't just maths. There's something different. It's a subject in its own. And it started off as a diploma. There was only enough material to cover 1 year's worth of stuff. And then it ended up as a full computer science degree in about late 1980s. And that degree, as I said, Cambridge calls these degrees triposes, tri-3. Tripos is a three-legged stool. Let's not go there, but never mind. Now, since then, there have been other things that we have done. There's actually quite a few. I'm not going to go into the details of them, but I would imagine, at the very least, everyone in this room would recognize Raspberry Pi. Whether you've used one or not, you would recognize that this thing exists. And that was our push to get people able to access it at all levels. So very cheap computing, get people programming, etc. And it has been, of course, very successful. I imagine many of you have used Raspberry Pis and will use Raspberry Pis for that matter. Okay. The good news is, although we have this big history, 90 years, which, by the way, is like really recent from a Cambridge perspective, but 90 years is still quite a long time. The good news is we have a different building now. The good news for you, the reason that's good news is because sitting on 90-year-old seats for lectures for an hour or 2 hours or 3 hours isn't much fun. I've done it. These are much more comfortable. So we have a much, what we hope is a much nicer environment now. We have this whole building. We do our best to entertain students and to make it a very relaxed atmosphere. And I hope that today you get an opportunity to walk around. There's an opportunity to do a self-tour, to take yourself around the department, just get a feel for what's going on. We don't really have the students here at the moment. PhDs we do, but obviously undergraduates have gone at the moment. So you don't get the full feeling of the sort of buzz of the place. But then again, you yourselves will provide some buzz today. Okay, let's talk a little bit about computer science as a subject and what it is today, because I think and probably, if I'm honest, this whole section is a bit more aimed at the parents, because we've also got to convince them that it's the right thing for you to do. So what actually is computer science? It's surprising how many people do not understand what computer science is. You will, I get that, but a vast number of people in the world don't really fully understand, and even you probably don't, or probably wouldn't have produced the slide that I've now got up on the screen, because you wouldn't have put things like psychology necessarily and philosophy in there. But these are all parts of modern day computer science. Everything that obviously maths is in there, sciences are in there, engineering, all those things you would all have gotten. Things like psychology, where does psychology come into? Well, you have to interact, you have to use these things. There is an interface, a way of working with this thing that you are building, this system, this computer. That's psychology. Getting something that's actually usable and workable, that's psychology. Philosophy, well, there's all sorts of stuff around information and logic, etc., and thinking about the world and abstracting away in different ways. Things like linguistics. It used to be that I had to explain why linguistics was a difficult match to computer science. Not so much these days because of all of the LLM stuff that's going on. Linguistics is a more obvious thing. And ethics is a very big thing, of course, that you have to have in computer science these days. Now, I want to take a step back from this and just point, that's a lot of things that cross into computer science. And if you compare that to most other subjects, in fact, possibly all other subjects that you can find in this university and others, there aren't many you can find that have this level of overlap with all the different things that go on. And it's not just the things you teach, it's the skills that you learn when you are a computer scientist. Some of these, again, you would have come up with very easily. Programming, for example. Yes, you've got to program if you do computer science. But there's lots of other skills. It turns out these skills are hugely transferable. What we have discovered is that all our graduates go off and do great things. But when we look at all of the different spaces they go into, all of the different industries, etc., that they might go off and do, we've probably got a graduate that's doing anything that you can think of. Even esoteric stuff that you would think that's got no link to computer science at all, we've almost certainly got a graduate working there somewhere in that space, because this is so transferable. The way you think, it's teaching you to problem solve more than anything else. And that's hugely valuable. It doesn't matter where you go. And these days, everything has to be scaled up. Everything has to be big. You have to go from small to big to get anywhere. Well, efficiency, scaling, thinking about how to solve stuff is critical. If you are an employer, yes, it's nice to have someone, an employee, who can solve problems for you, obviously. It's also nice if that person can solve them efficiently, because that will give you loads of savings. That's the kind of skill that we train people to have through computer science. We have to talk about employability, if nothing else, for the parents. And you will be fully aware that computer science has traditionally, in the past, had really large tech companies, they obviously still exist, and they're doing exciting work and they offer enormous salaries. Well, absolutely nothing has changed. These exist, the salaries are huge. I will be honest and tell you that almost every graduate I've had for the last few years has walked out into a job that has a higher salary than an academic would have, so higher salary than me. But that is the way this world works, okay? Nothing has changed, it's super employable. And you shouldn't just believe me, this isn't for computer science specifically. Even if you didn't believe the computer science side of the things, well, just going to Cambridge, it turns out, makes you hugely employable. These, the top one there, THE from the Times Higher Education, is this year's. I think the Telegraph's from last year's. I just couldn't find anything that they were saying this year. But it basically puts Cambridge at the top. Now, obviously, you'll be aware there's all sorts of university rankings of the university, of the subjects, and all sorts of things that come out. And then the newspapers love to say, oh, Cambridge dropped one or went up one or all that stuff. That's irrelevant, right? Top 10 is irrelevant. Having said that, that's number one. Okay, so bear that in mind. So we're talking about subject here, teaching you great skills, making you very employable, and Cambridge on top of it, which boosts that employability. I'm going to really drive the point home now. Every year, we have a careers fair, and we ask companies, we offer companies the ability to pay for a small stall. You can see these tables here, and they do it outside this lecture theatre. They line them up there, and we simply say our students will come, and you can talk to them about the job offerings that you might have. We get, well, we can only squeeze in over 2 days about 100, 110 companies, so we actually have to turn some companies away. That's what we can squeeze in. And you go and talk to any one of these tables and you say, well, what are you here for today? Oh, we're trying to find great graduates. How many are you trying to find? We're trying to find 2, 3, maybe 4, okay? So there's 100 companies in 2 days, 48 hours, let's say 3 on average places that they're looking to fill with great graduates. That's 300 jobs. We have 130 graduates. It's a bloodbath, okay? They're desperate to get people. And this is just the companies that are coming on those days. There's many, many more companies, and they're not small companies, right? You might be thinking these are just local startups. We have startups. Some of you will even go on to do startups in Cambridge, I'm fairly certain. But, I mean, the sort of companies we've had here are Google, Disney, BT. These are big, big companies looking for the graduates that we can produce. And they think it's worthwhile, knowing that they're only going to ever get 1 or 2. They think it's worthwhile making the trip, paying the money, and doing all this for this period just to get the people that we produce. So let's talk a little bit about what we actually teach and give you an idea about why they are interested. And before I start going down this line, I just want to make one comment, which is we obviously review everything that we're doing. This is a really fast-moving subject. You know, technology moves. The reality is technology will be different at the end of your degree than it is at the start of your degree. Now, so everything I'm going to present now is a snapshot. It's a moment of what we are currently teaching, and it almost certainly will map very much to the first year when I talk about that. But by the time you lot would get through to the third year, we probably will have made some changes because that's what we need to do to stay on top of things. So don't read too much into the actual specifics as we go through this, but get a feel for what we're doing and how we're trying to teach, because those things will carry through. But the reality is we will also be evolving our course because that's what you need to do in this world. Now, if you ask people, why would you do computer science in Cambridge? What you often get told is, oh, yeah, that's a theoretical course. They do theory. I think that's a bit of a misnomer, but it is important to recognize this. The roots are in mathematics. The Tripos probably gives you the strongest grounding in theoretical CS there is in the country. I say that without having done any particular research, but I'm fairly confident that's going to be the case. We are very theoretical, or at least we offer very theoretical points. The reason we do that is because this is the underpinnings. We have to build up students, graduates, who are able to cope with the future, not just cope with the future, sorry, but actually create the new future. When the next piece of technology that's game-changing comes along, whatever the next phone is, that was a huge change to computer science, to just go to things where they're in your pocket, everybody has them always connected, right? Massive change. We couldn't teach that before phones came out, but our graduates all found it easy to make that transition because they had the core basics, the fundamentals, the principles in their heads. That comes from some theory. You have to have theory. So this is really critical. So it's very important that we do this. This gives you the long-lasting stuff that isn't going anywhere. The mathematics, that fundamental principle, is still going to be applying in 100 years for the technology, still all going to be relevant. The actual technology part of it, of course, will have changed. But I think it's a little bit unfair because often you will hear, oh, it's the theoretical course. It is theory. That's all they do is theory. It's nonsense. Because actually we do practice as well. You have to learn all those skills that we showed you before. You don't learn skills by listening to someone at the front of a lecture theatre. You learn skills by doing things. You don't learn to program well by reading about programming languages. You learn to program well by doing it, making mistakes, understanding the problems, makes you appreciate all the tools that are available to you. And so we do a lot of that. You'll see throughout of our degree, what we're doing is we're trying to push people to do stuff as well. You will be taught the theory, but you'll also be asked to implement some of the theory, to program that, to test that, to build that system. So we really do emphasize practical work throughout that tripos. And I'll come back to some more specific examples as we go. Okay, so now we get to some more stupid Cambridge nomenclature. 3 years for a degree. And for fun, it's also a BA degree, Bachelor of Arts, because that's all Cambridge gives out. It does not give Bachelor of Sciences, just gives Bachelor of Arts. So 3 years for a BA, that's the first thing that confuses people. Then the second thing, 3 years, what are we going to name them? Well, let's call them first year 1A, let's call the second year 1B, and call the third year 2. Okay? I'm convinced this is an IQ test that we sort of like to do in Cambridge. We just like to feel superior because we can understand there's some sort of translation going on here. And we're going to talk about each of them. So first year, you turn up, and what we find is that everybody has a very different starting point when they're here. Some people have spent all of their time doing mathematics, and they're amazing at mathematics, but they're probably not as good at some other aspects. Let's just take one, say, programming for a second. Other people come and they haven't spent their time doing all the mathematics, they've spent their time doing the programming or doing some other aspect of computer science. All of that's fine, but from a perspective of teaching, we have to make sure everybody is at the same level. So a lot of the first year is about teaching people all of these fundamentals in programming, algorithms, a bit of electronics, and the maths particularly, to make sure everybody is at that base level. We've all got some level of understanding of computer science that we need to build on. That's all of our first year, really. And if you delve into what it looks like, well, Cambridge likes to think of courses in terms of the exam papers you do at the end of the year. Cambridge is based predominantly on a system of synoptic exams, end of year, you sit exams. You're familiar with this for GCSEs and A-levels. Please do not read too much into the specific courses. They're just there to give you a flavor. All we do is we divvy up some courses across these papers. Very, very roughly, the first paper there is sort of on programming and a bit more of algorithms and implementation thing. Second paper is a bit more towards systems and hardware. The third paper we consider to be more about applications. And because I know what you're thinking already and what you came here and wanted to hear, yes, there is some machine learning right from the get-go. Okay, so even in the first year, there's machine learning there as well. The other thing to point out is there is 1/4 of the year that's allocated to maths. We currently borrow that paper from natural sciences. So it may or may not interest you, but if you have friends who are looking for physics, chemistry, whatever, there's just a huge number of people that do this same course on mathematics, and they come from all of those different subjects. We also do that at the moment. So for one paper of a year, of the first year, that is 1/4 of the year is associated with this maths course. And when we talk about maths there, it's probably more what you have done when you talk about maths, so what we would call continuous mathematics, differentials, all of that kind of stuff, versus the other type of mathematics, which is particularly important for computer science, and you'll see it in here, discrete mathematics. Okay, so having done 1A, you're all at a good level. We now got to go to the second year, which again is not called 2, it's called 1B. This is core. So our goal is that when you finish 1B, you have got a baseline understanding of every single aspect of computer science. There are no options. You can't escape. You can't say, I just don't want to do the maths for computer science because we don't think that makes good computer scientists. Everybody has to have a baseline knowledge of every single part of computer science, and that's what we focus on in 1B. We tend to think of it in terms of theory, systems, hardware, and programming, but they are just all a whole load of courses, and I've got a list of them here. Ooh, it's gone off the side. Sorry about that, but never mind. Don't, again, focus too much on what the actual courses are. The point is there's a huge diversity here. We're going from distributed systems to the semantics of programming languages, okay, to detailed, actually, what we got, complexity theory, for example. That's detailed theory and mathematical understanding of computer science. You need to have the lot, so we make you do the lot. That is what we do in our second year. Another interesting part of the second year is the group project. This came about because we talked to industry about a decade ago, and they would tell us that, oh, you've got wonderful graduates, they're so smart, they're so amazing, but they don't know how to work in a team. And what's the first thing you need to do when you go out and work in industry? You need to work in a team. So one of the things we're trying to do, or have been trying to do, is to boost some of that. And this is an example. So the group project is where we take the whole year group and we slice it up into small teams of about 6 or 7. Those teams act like a consultancy, an external consultancy. We then have companies come in, one person from a company, and provide a project to do, as if it were a consultancy. And then you have to interact with them like a client, and you have to work with them to produce something interesting. This goes on for a whole of a term, which is about 7 or 8 weeks. And what's incredible is the stuff that comes out the other end is just amazing. It's the things our students do is just fantastic, because they learn to work together. They learn to collaborate to get things done. And there are all sorts of examples. You can go top of the building, far end, there's a whole load of videos, because every time they do it, we ask every group to record a short video describing what they've done and what they've achieved. You can go and watch a whole bunch of those videos today. But just briefly, there are things like this. So this was autonomous vehicles. They wouldn't give us autonomous vehicles to actually play with, it turns out. But we were able well, there was a client that was able to build algorithms for following vehicles and make sure the crashes and all sorts of things. And you could simulate it with these little things. This is my all-time favorite one. This is a self-playing chessboard. The way that worked was there is a chessboard, obviously. Underneath, there was a robot arm with an absolutely enormous magnet. And you can see the white things around the chess pieces. That was just wire curled around and then some tape on there. And they had to program it to play itself using this magnet, which is a lot harder than you think it would be. Because if you imagine, you can't lift these things with a magnet. You have to scrape them around. So you had to plot courses and make sure you didn't knock different things over. Very, very cool, and it worked. Okay, so that's the sort of thing. And that was achieved in the space of 7 weeks as a cool project. And I do think that was a very cool project. Hard to do, but very hard, because you've got to think about the algorithms, you've got to think about the hardware. So many different pieces had to come together, 6 or 7 people, and they did it. Then we get on to the third year, which, as I said, is called part 2. This is where we do allow you to specialize and take some options now. Okay, so before we were saying, no, you don't take any options, you have to do everything. This is the point where you start to say, actually, I would quite like to specialize. Or interestingly for us, you actually get an opportunity to not specialize. I'll come back to that in a second. So how do we split that year up? Well, unlike the other ones, which were just straight exam papers, we're going to split this one up and talk about different parts of it. Half of the year is covered by 2 exam papers, normal standard type exam paper with a lot of choice on. Those map to normal courses, if you like. Now, here's my point about specialism or not. If you go to some universities, you have to make a decision in your final year and say, hey, I'm going to do machine learning. And then all you do is this stream of machine learning. Or I'm going to do theory, and all you do is that stream of theory. That is fine. You can do that with us because you just pick the right courses. You can also, however, say, do you know what? I don't want to limit myself. I would really quite like to do some machine learning. I also want to do quantum computing. And you know what? I want to do business studies as well. It's fine. We let people choose whatever they want to do. So you don't have to specialize in that very narrow way, but you can if you want. Those are, let's call them normal courses. You do the lectures, you do the work for them. At the end of the year, you sit one of these 2 exam papers, which tests you on those things. We also have introduced these things called modules, which are a little bit different. And at the moment, the way that it works in part 2 is you choose 2 modules. So again, choice. These are in-depth courses. And unlike the other things where you do lectures and you do an exam at the end, we actually say to the teachers, the lecturers of these courses, you can decide how you want to assess this course, but you assess it within the course. So there'll be some who'd say, well, that's fine. I've got you for so many weeks. And at the end of those weeks, we will do an exam. I'll make you sit down and I'll do an exam. There are others who say, well, I'm going to give you an exam every week, a mini exam every week. And there are others that say, well, actually, I think the best way to assess my thing is something practical. I should give you an example. We had a course on building a network router, like from the ground up. You had to do that. And the whole goal at the end of it was to just build the new router. You wanted good marks? Build the router. It wasn't an exam. It was like, let's see how well you've done it. Let's see what stats you can produce from this thing. Right? And that's because the lecturer in charge is saying, this is the best way to assess the thing that I am teaching. That's what we allow with our module. So you get to do 2 of those. The last thing, very common for, at least for UK 3-year courses at the end, you do a project which runs the whole year. As an individual project, so this isn't a group project. And at the end of that, you produce a roughly 12,000-ish word essay or dissertation, and of course that gets assessed. And the way I've laid this out should give you an idea of how important each component is to the year. So 1/4 is a dissertation, 1/2 is the papers, and 1/2 is the 2 modules together. Again, I'll refer you back to my earlier comment that things may change by the time you get through the tripos, but this is how we do it at the moment. Okay, so if you pass those 3 years, which obviously you would, then you graduate with a Bachelor of Arts degree in computer science. Okay, so again, Bachelor of Arts, it's just a weird Cambridge thing, don't worry, no one cares in the world because no one understands. Now you could graduate with a BA, or you could go into part 3, which is our 4th year. However, there are some things you need to understand. First of all, you have to decide to go into part 3, and we have to decide to let you go into part 3. So at the moment, making that transition requires you to get a first in part 2 to go into part 3. And again, part 3 is the 4th year. Out by 1 error is pretty common. So we get a first in part 2, you get into part 3 if you wish to. That year is actually really, we think of it as preparation to do research. So we're actually going to push the boundary again. We do think, well, we do give you another project to do, another dissertation, but this time it's a project that's on research. So think of part 2 as we try to take you on, in certain subjects, we take you all of the way to the bounds of the knowledge on that thing. And then in part 3, we try and push you over the bounds of that thing. Come up with something novel, see how you do. Learn about how we do some research and how new things get discovered in computer science. That's what part 3 is focused on. We often internally call it a 0th year of a PhD, so it kind of gives you an idea. I will do a special mention for AI, because if I don't, I'll have a queue of people at the end who want to ask me these questions. So artificial intelligence of all types is a really key part of modern computer science. And you have to be both proficient in the use of it, and that is very important again, but also you have to understand how it works under the hood. Future AI systems are going to come from you. You are going to be the ones that develop it, but you won't develop it if you don't actually understand how the current ones work. So there are 2 ways you can use it as a tool today. You've probably realized you can go and build yourself all sorts of machine learning models very quickly using Python, just by sort of putting a few lines of Python together, because all of the clever stuff under the hood is being taken care of for you. It's important that you can do that, because that's like just a life skill these days in computer science and beyond. But it's also really critical that you understand what is going on under the hood. So we will be teaching both. We teach you how to use it, the practical skill, but also how to actually do the underlying stuff. And you should ask that of every course that you're looking at. Make sure they're not just teaching you to be using the technology, but actually understanding the detail. I get asked a lot about what a typical week looks like. I don't think there is a typical week. I ask my students, they all come up with different answers. But broadly speaking, I think this is what we've landed at. There's very few teaching weeks, only 20 a year, less than half the year you spend being taught in Cambridge, with 3 weeks of exams, actually 2 weeks of exams for computer science. And we cover, when you compare the syllabuses, we actually cover a lot more than other places do. So you cover more in less time. Guess what? It's going to be quite pressured. That is Cambridge for you. The workload is high, the pressure is high, but the payback is huge. All the stuff we said about employability and your just general abilities are in there. If there is a typical week, I guess 12-ish hours of lectures, 12-ish hours of consolidation. At least that's what my students tell me they do. They think they lie. I think it's much less. And then we have these supervisions, I don't know, 2 to 4 supervisions a week. And we say nominally 5 hours of preparation for each. But to be quite honest, these numbers are so variable, so dependent on you, so dependent on the subject, that I don't really think it's useful to give these numbers particularly. But everyone keeps asking for them, so I'm just giving you a broad, sweeping idea. All right. So after all of that tedium, we now get to the bit you actually came for, which is how do you apply? It's not the easiest of processes, and I'm going to be upfront with you and show you some numbers. Every picture tells a story. This is what has happened to the number of applications we have had every year since 1999. Okay. There are some very interesting trends going on here. And I know you're all too young, and it makes me very sad that you're all too young because it means I'm too old. But back over at 1999, 2000, this was the dot-com bubble. This thing, which is now probably taught in your history lessons, almost makes me cry. This is where everyone thought the internet was going to be amazing and made really bad choices about their businesses on the internet, didn't really have good business models, but everyone thought it was amazing, pumped loads of money into it. Everybody thought computer science was the way to go. Loads of people, we see this rise. Then what happened is all these companies had terrible business models. They all went bust. Everyone said, oh, okay, this internet thing's just a fad. It's just a waste of our time. Stock market crashed. No one cared anymore. You can see that it's sort of coming off down here. And then a very interesting thing happened. We started to see some phoenixes, I don't know, arise from the ashes. Google's, Facebook's, these big tech companies that we now recognize and that you use probably every day, started to come out and show that, oh, there are business models that can work. This is a sustainable thing. And suddenly people started to say, well, hang on then, I want a piece of this. They're suddenly doing quite well. And we see this trend rise and rise. And unfortunately for you, rise to quite a high number there, right? 1,875 people applied to do this course last year. What should you take away from that? This is a popular course. This is a competitive thing to get on, and it's for all the reasons that I've already shown you in this lecture. The next slide you're going to hate, and I apologize for that, but I'm now going to take this and I'm going to overlay the number of people who actually got in each year. Now, there is a problem that many of you, even though you're very intelligent, do the thing where you go, okay, 125, divide it by 1875. What's that? About 7%. I've only got 7% chance of getting into Cambridge for computer science. And one way, I mean, if you like statistics and think statistics, that is the right way to go, then I suppose I can't argue with you at some level, but that assumes that it is a random process. This is not a random process. Okay, this is a competitive process. There will be many people in that 1875 who are just chancing their luck. They don't have the grades, but they're going to try anyway because, hey, if they could get in, wouldn't that be amazing? So it's not that everybody is equal here and it's some sort of random selection like a lottery and we choose 125 people. Therefore, please don't fall into this trap of looking at numbers like this and thinking, that's my chance, therefore I shouldn't apply. If you're good, then you would be stupid not to, in my view, you'd be stupid not to try to get into this number. I will also just show you that red line without the blue because it does show some trends. Otherwise, it just looks like it's flatlined. It hasn't flatlined. It's actually showing very similar trends to before. There's a bump here and there's a rise over here. I won't go into the detail. There's a reason why Cambridge can't move very fast in terms of increasing numbers in the way that it works. But we are on a trend that's going up, and the university is now supporting us in having more students as years go on. So let's talk about what you actually have to do if you're going to apply and get in. First up, by mid-October, you know this bit, you have to have a UCAS application. If you apply to Cambridge, we send you a supplementary questionnaire and we ask you some extra stuff. There are tons and tons of web pages and information on the generic Cambridge stuff. I am not going to focus on that today. Okay, if you want to find out more about that stuff, then by all means go and have a look at the website. I'll talk about the computer science specific stuff. So at this stage, what do you actually need to know and do? Well, here's a new thing this year that you may or may not have been observing. So first up, our standard A-level offer, A star, A star, A. That shouldn't be a shock to anybody in the room. There is, however, a change on maths this year. So we've always said, if you are doing A-levels, you must have single maths, or maths as it is properly called, but single maths as we refer to it colloquially. The new change is that if your school is offering any form of further mathematics at A-level, you are required to do it. We need that for the application. This comes because when we reviewed everything, maths is a pretty good determinant of how you're going to do in the degree. And also when we looked at the people who we were selecting, without looking at what they were doing, we found that they were naturally having more mathematical skill and doing further maths anyway. So if your school offers it, then you're required to do A-level maths. If your school offers it, you're required to do AS level further maths. If your school does not offer these things, there is no requirement for you to do anything. And I know that there are a number of schools that do not. And from my experiences yesterday, what this slide is going to do is give me a queue of people at the end of this lecture going, oh, I didn't know this and I didn't take further mathematics. So there are some options you can try. I will be honest with you, the right way to do this is to go and talk to the college that you're going to apply to. We've got that in a couple of slides' time. And say, this is the deal, and this is what I'm going to do to make sure I have more mathematical ability for when I arrive. And you'll have to discuss it and make sure that they would be willing to at least consider you to the next stage. Okay, so that's our big change. If you don't do A-levels, if you do other stuff, well, I couldn't put them all on the slide. So the right thing to do is to go to the CAMAC UK website. It actually has a nice page where you can say what qualification you're doing, and it says what the matching necessary things are. Broadly speaking, though, our take for computer science is the more maths you can do, the better, because that translates to better computer scientists down the line. You'll notice I did not put computer science was required. It is absolutely not required, but there's a caveat here. It would be incredibly weird to have a candidate today who turned up in front of me and said, I want to do computer science, I'm going to be amazing at computer science, but I've never even programmed. 20 years ago, maybe even 15 years ago, that was relatively normal because people didn't have access to the systems, didn't have a computer necessarily of their own to do this stuff. Now we've got Raspberry Pis, we've got schools doing it, it's everywhere. So to come and say, I have never done any programming is weird. We saw how competitive this was. You want to stand out, I'm going to tell you something, you're probably not going to stand out through your grades. Right? Everyone's going to offer us probably a whole bunch of A stars. Everybody is going to be doing the same thing. We just got this big pool of more than 125 people who are going to, on qualifications alone, you can't pick them. So what else are you going to do? How else are you going to convince us that you're the right choice for taking? And you know, you should be doing stuff in your own time. If you are doing a qualification, that's great. It doesn't stop you from also doing some extra stuff in your own time. Really, it's all about showing that you have a passion. And it would be so strange for someone to turn up in front of us and say, I haven't done programming today. And for us to say, well, you're applying to do a degree that's competitive and has loads of programming in. You're just saying for the next 3 years, you want to do lots of programming, but you've never even tried this. That's just weird. Okay, so I'm sure there are very few, if any of you, that are not doing something at this point. I would also point out there's plenty of time between now and coming to do lots of stuff if you're not doing much. Some of you will come and ask me about colleges. It's a weird system in Cambridge, as ever, historical. Colleges actually handle all the undergraduate admissions. So technically, they have some autonomy in everything, in every decision that is made that of who they admit. That's a little bit weird, and it does mean that there can be slight differences between what you get when you apply to one college and what you get when you apply to another college. They are small, but they are in existence. You will then undoubtedly come and ask me, what is the best college for computer science? And that's just the wrong question. Can't tell you. I would be very, very wrong if I tried to answer that question. The question you should be asking is, which college is best for me? And I can't tell you that because I don't know you. Not yet, anyway. So you have to decide what the right college is for you. You have to make a decision. Yes, you might like 200-year-old architecture, or 800-year-old architecture in some cases, beautiful, great spires, wonderful things. Or you might like plumbing that works. Okay? There are many different choices. What do you want? Where do you want to be? What is the atmosphere that you like in a college? Do you want it to be super competitive? Do you prefer to be more laid back? Do you want to be in a group of 20 computer scientists in a college? Or do you want to be in a group of 3 or 4? They have pros, they have cons. Right? There's no one size fits all. You unfortunately have to make a decision. And it's really hard, I get it, because you don't know the colleges. It's quite hard to get a feel, but there are things you can do. You can talk to the directors of studies. Some of them will be here today, and you should make use of that on the top floor today. You get a feel for a college. You can talk to the students. Now, they've gone. Well, some of them are around, but most of them have gone. But in this wonderful world of social media, it's not difficult for you to track down groups and stuff and ask people, you know, what do you think of the college? How does it go, etc. Use everything at your disposal to figure out what works for you. In truth, very few people get to a college and decide that they don't like it to the point that they hate it. But the best college for you, we can't tell you that. Okay, you get a feel for it, have a look around them, talk to people, etc. Sorry, that's not what you wanted to hear. You wanted me to tell you what to go and do, but I can't do that. There is also a personal statement at this point as well. And you have to write this personal statement. Now, this is your chance to tell us your passion for the subject. A few years ago, about 5, 6, 7 years ago, there was a period where I could predict what a personal statement was going to look like, the structure of it, without even opening the page. I knew paragraph 1 was going to say, oh, I love computer science and I've been doing it loads at school. And paragraph 2 was going to say, oh, I read this book, blah. And I thought it was amazing. And I just thought it really inspired me. And I knew that paragraph 3 was going to say something about what they do in extracurricular activities. How did this happen? Because the schools thought there was a template for how to do this. And it was awful. And guess what? When there's a template, we're not going to use that so much, right? We want to get it from you. Use the personal statement to convey your passion. Why do you want to do computer science? Why should I rank you above the other person with exactly the same qualifications as you? Right? What is it that makes me think that you are going to be a good choice to go and do 3 years and come out and really change the world with computer science? That's your opportunity in the personal statement. Tell me all the things you've done. Don't just tell me, oh, I made a game. Right? Great, you made a game. We might talk about that in the interview. That's interesting. But tell me what the hard bits were. I made a game. And what I discovered was it was really, really difficult to make the refresh rate on the screen work well enough for the speed I was doing it. So I came up with this clever idea, or I read around and I found this algorithm that could speed it up. And I got it 4 times faster, right? Just writing that, no more detail than that. That's brilliant. That tells me loads of stuff. It tells me you're interested enough to do this. It tells me you can go and research some stuff. It tells me you've got an understanding of what was actually going wrong with the problem, right? What was going wrong with your program. It's great. That's the sort of thing we want to read. Don't tell me that you've read a particular book and that you loved it unless you know that book backwards. Because I tell you, the number of times I've had people say, oh, I read this book and I'm reading that thing. That's a university level book. That's impressive. Right? And then I talk to them about the interview and I realize within seconds, they do not understand a word in that book. Right? They might have read it, but it's beyond their level. They don't get it. And there's no reason for it. The only reason they put it in there was the school said, it will look really good. It's not about that. Give us some passion. If you want to write a paragraph in your personal statement and it conveys the passion, that's fine. You want to write an essay, that's fine too. Not too long, please. There is no magic format, despite what your school may or may not tell you. There is no expected structure. There is no expected length, but there is one expectation. You've got to convey your passion to me and to all the other universities that you're applying to. Okay, so we get to this point. We've done the application. Then in October, you have to sit the TMUA test. Now, there is a big, big change this year, and I need to really convey this. This is the big change. We have got someone else administering the test. It's gone to a different company to administer the test than has happened in the past. Your school may not be aware of this. What is really changing, more universities are using it. They've actually decided to do multiple sittings in a year. But if you're going to apply to us, you must take the first sitting, which comes in October, not the one in November or whatever. It's too late for us. You have to take this particular sitting. And if you're going to do that, you have to take you have to make your application to do it, your registration, sorry, by September the 16th. Okay, it's critical. You can't miss this one, right? This is critical, and this is different from previous years. You have to register by September the 16th to take this sitting. Other universities will be using the TMUA, not all of them. And of course, you only take the thing once. So you just take it in that sitting. That will also be what gets used in your other universities if they're using the TMUA. The other big change is, yes, there is a cost. £75 from the UK, £130 if you're coming from outside the UK. But this cost can be completely covered, 100% covered, by a fund that's been given to the company administering this. And when you go and look at the website for the TMUA, up the top right there, you will see that you can apply for a bursary. You're actually supposed to do this before you go and do the registration on September 16th. What is that bursary for? Well, it's basically you've got to show that you can't fund this or that you just don't have the funds to go and sort of outlay on this. Right, so it's up to you. You'll have to demonstrate that stuff, but then there is a voucher you get that covers the whole amount if you do that. So it's pretty important to understand this is something you've got to do. What does the TMUA look like? It's a multiple choice. I'm afraid it's hard multiple choice, so don't sort of breathe too much of a sigh of relief. You can go and look online on the website. They give you tons of information, past papers, all sorts, loads of practice stuff. Really good practice. Actually, just even for the interviews, it's quite good practice. In multiple choice, but it's hard multiple choice generally. You just go around, you just have a look, 2 papers, 75 minutes each. One paper is on mathematical knowledge. One paper is on reasoning. Okay, so you've done the test. There are two outcomes at this point. One is the unfortunate one. It is possible that you get rejected. That might be the end of the line for your application. If you're lucky, or if you've done well, as I'm sure many of you will, then you get to go to the interview stage. This is the scary bit, right? Everyone's scared of the interviews at Cambridge because you've read some of the media stuff. Most of the media coverage of Cambridge and indeed Oxford interviews is complete nonsense. It's a lack of understanding of the reporters for what the question is for. So they pull out silly questions. So they say, look at this stupid question this person got asked. I often read those questions and I think, that's a good interview question, right? Because I can see how it gets used. What are we doing in our interviews? It is not about, let's give you a stupid, really hard question and sit there and smile at you while you sort of squirm, right? That's what you might think. It's not about that. It's actually about understanding how you think. How do you try to solve a problem? Because that tells us so much about how well you'll do in Cambridge. Everybody starts a question with a different base knowledge. It's quite funny. You always ratchet up the question. And I can see, because people do stuff from just knowledge, they have memory of things. You start asking questions like, what does this look like? Oh, looks like log, looks like this, looks like this. Okay, I'm just thinking, this is telling me nothing. No information is coming across at this point, because really all you're doing is regurgitating what you know. At some point, for every single one of you, we get to a point where you do not just know the answer and you have to think. Different people will end up at different points. It doesn't matter, because that's the thing that I start watching. That's the moment when I'm starting to say, what's this person doing? Some people go, I don't know that. Can we have the next question? Those are the people that are not going to do well in Cambridge. Some people, I don't know that, but it sounds a bit like something that I've done before, so why don't we try going down that line? I just have a go, right? That's the sort of person that does well in Cambridge. We're looking for that thinking, and we're going to steer you, right? We're going to let you go, and okay, that was the wrong way to go. It's interesting to see. Let's steer you back a little bit. Let's see what happens if we just give you a nudge. Bizarrely, from your perspective, it probably isn't that important to us what the final answer you get to is and whether it's right. I don't care as much as how you tried to get there, because that's what tells me loads. We do this with interviews, 2 25-minute interviews. You can sort of understand the things I've just said are hard to convey in an exam paper. We can't extract that from the Temua. So it does give us bits of information. It is important to us. So 2 25-minute interviews. And then, oh yes, sorry. Some colleges do have additional tests, written tests on the day. Not very many, if I'm honest. And it's possibly, the answer is even 0 for this year. I'm not sure. Very few colleges can do it, but they do, in theory, have the ability to do an on-the-day test. I know one college that likes to do a test, written test, but then when you go to the interview, they want to discuss what you wrote in the test, what you actually did. So that's one way in which an interview can work. Now, in order for you to know what it's going to look like exactly, you have to look at the college. You have to talk to the admissions office of that college that you're applying to. Right, at this point, you've got almost all the way through the process. You could have been rejected, and unfortunately, you could be rejected at this point as well from the interviews, but you could also get to an offer. We could say, yes, get A star, and you're in, right? You can give that offer. There's one other thing that can happen, and that is you can end up in the pool. So we can say, our college can say, look, this person looks like they're good enough. They look like they've made the bar. Unfortunately, we haven't got space. So you put them in the pool, and other colleges can come who have got space, and there's always colleges that have got space, and they will come and they will look and they will say, oh, this person looks really good. Actually, we would like to take that person, and they could make an offer. So the whole thing completes by about mid-January, and that is the whole process of application. It's quite involved from your perspective and from ours as well, but this is how you get into Cambridge. The tip really is that you just do everything that you probably already know. So again, Cambridge, great. Computer science, great. Employability, really great. And you should apply. And that is not a joke. If you're sitting here in front of me, by the way you are, then then you must be here because you've made a journey. You've made a journey that wasn't worth making if you're not going to have a hope. And I do not understand why you would not try if you have a hope of getting in. You have nothing, zero, nothing to lose. And I can tell you that me personally, I did not think I was going to get in. I had a crack at it. I'm not coming from a private school or anything like that. I thought, no real chance, but what the hell? I've got some grades predicted that are okay. I went for it. I got lucky. I did the thing where you flick the book, you go, oh, I'll just use that college because it doesn't matter. I'm not going to get in. And then I got in. And unfortunately, I've not been able to escape after too many years that I don't want to say. So please, if Nothing else, just apply. You have nothing to lose and it could set you up for life. Just do it, okay? Otherwise, you will always spend your life thinking, I wonder if I would have gotten in, okay? Just do it. I'm going to finish now. Thank you very much. And one last thing is please do look around the department, and if you go up to the top floor, you will be able to talk to many people, directors of studies and other things like that, who will be able to give you lots of answers to your questions. Thank you all.